For the last few days, we've been talking about simple harmonic motion, springs, pendulums, things vibrating back and forth, and they do that with a very regular, very repeating pattern. And essentially, the whole point of that is to get us familiar with this idea that things vibrate, and it happens regularly, and it repeats, and we can take that and we can apply it to more than just a simple pendulum or a vibrating mass, which many things oscillate, like the way musical instruments work. It's a vibrating string a lot of times, or a vibrating membrane. Your ears work because your eardrum vibrates. Okay, so a lot of the motions and things we deal with are with vibrations. But the reason you can hear me right now is because my vocal cords vibrate the air around me, and that's transmitted to a microphone that in turn vibrates, causes an electrical signal which is transmitted as an alternating current, which is a vibrating electrical current, into the computer, which codifies it, and then the whole process happens in reverse so that you can hear me now. Okay, so how did this vibration right here in my vocal cord get from me to you? Well, it was all transmitted by a wave. Okay, and there's a couple different kinds of waves, but they all have the same thing in common. Waves are not matter. Waves are the transmission of energy, and it's caused by a disturbance. Okay, so waves and vibrations go hand in hand. Okay, a vibration or an oscillating source is what causes it. Okay, and so the reason you can hear me now is because my vocal cords vibrate the air. That causes the air to actually call compression rarefact, and then that goes to the microphone or to your ears or whatever. And so this transmission of energy is a wave. Okay, and the source is a vibration. So if we can understand how a source vibrates, maybe we can understand how a wave moves, how it's able to go through space, or go through ropes, or go through water, right? It doesn't matter if it's a wave on an ocean, it doesn't matter if it's a wave on a string, it doesn't matter if it's a light wave. They all have some very similar properties, some similar characteristics. Now, for now, we're just going to focus on mechanical waves. And a mechanical wave is a wave that actually requires a medium to go through. Okay, so that's what this says. There's two major types, mechanical and electromagnetic. Scientists are inherently lazy people, so this will be like the only time I ever write electromagnetic out. The rest of the time I write EM. But mechanical waves are waves that need something to go through. Sound is a mechanical wave. It needs air to go through, or water, or a solid, but it has to be there. Light is not a mechanical wave. It can go through a vacuum. It doesn't need anything. It can go through nothing. Okay, we're going to focus, like I said, primarily on mechanical waves. They require a medium. The medium is the stuff that it moves through. Electromagnetic waves do not. They can go through a vacuum. And the reason they can do that is because they're fields that vibrate. Okay, an electromagnetic wave actually contains two parts, an electric field and a magnetic field. And they vibrate at right angles to each other. And they propagate themselves. So the vibration of one causes the vibration of another. We'll get more into that later. For now, we're going to look at mechanical waves. And mechanical waves do require medium. They do require matter through which to move. Can be mostly anything. Okay? Some waves will only travel through certain materials, and we'll talk more about that when we get into longitudinal and transverse waves. But water can carry a wave on the surface or in the depths. Strings can carry waves, slinkies can carry waves, air can carry waves. There's all kinds of things going on. Okay. But no matter what, mechanical waves, they do share a couple general features. Okay. Any wave can move over large distances, and that's probably mostly demonstrated in an ocean or a lake. Okay. If you've ever watched waves come into the shore, where did those waves start? Somewhere else. Okay, a wave can go a very, very long ways, and they travel at a speed. Okay, it actually takes time for a wave to get from one place to another. It doesn't all happen instantaneously. Okay, so waves travel over large distances, but they do it with a particular speed. They're not instantaneous. It does take time for a wave to get from one place to another. Also, the wave does not carry the medium with it. Okay, I want you to think about like a wave going around a stadium. The way that works, everybody jumps up and then you sit back down. Okay? The people haven't moved. Their displacement overall is 0, but that wave travels around the stadium. Okay, so each particle of the medium oscillates about an equilibrium point, but the medium itself isn't carried. Okay? So that's once the wave goes by, the medium goes back to where it used to be. It doesn't get pushed into the shore. So the water that breaks on the shore when an ocean wave comes in did not come from the middle of the ocean. It's just that same water vibrating back and forth, back and forth, back and forth. Okay? Important things to keep in mind about waves, they are not matter. Okay, just because they're moving through matter, that does not make them matter. And there's some cool properties of waves that we're going to see that matter couldn't do. Okay, you can't have two objects occupy the same spot at the same time, but two waves can. Okay, waves are the transmission of energy. It's energy moving through something. Okay, and it's caused by a vibrating source. A disturbance somewhere is putting energy in, and that energy is transmitted through a medium in the form of a wave. Okay? So the vibrating source at one end transmits energy through the medium to an object at the other end. And that could be sound from me to your eardrum. It could be an ocean wave caused by a boat, and or whatever. If you've been on a lake and a big boat comes by, a few seconds later a wave comes by the wake. That disturbance is caused by a source that's oscillating or doing something with some kind of repetitive motion. Okay? Or it could be as simple as you throw a rock out in the middle and you still get ripples of waves that come out of it. Okay? So waves transmit energy. Now let's take a little bit of a look at the parts of a wave. Okay? And we're not going to start with a continuous. I know we think wave, we think a sine wave. But I want to look at an individual wave bump, a wave pulse, if you will. Okay? So that's this first part. Okay? The wave pulse is a single bump sent through a medium. Now, here's my picture, but let's actually go to an animation real quick. I'll show you what I mean. Okay, so this is a simulator that allows me to mess with some wave properties, and all these things up here mean stuff. We'll get to them eventually. I just want to show you a wave. I want to show you a single wave pulse. Okay, so I click this pulse button down here, and it causes this wave to propagate through this rope-looking thing. Okay, now I have an infinite wave, so it goes out the window and never comes back. If I start that again, okay, I'm going to pause this. Okay, you can see there's some interesting things going on. This side of the wave over here is moving up. This side of the wave on this side of the peak is moving back down. And that's because of the way this thing pulsed. First it jerked the rope up, then it jerked the rope back down. Okay, and so what we see is first the rope goes up and then it comes back down. And this is idealized, right? It's a perfect rope. I've taken off all friction. That's what this damping is. But it's the force between these particles that actually makes this wave travel, right? This particle right here is attached to this particle here. There's forces of attraction that holds them together. So as this gets pulled up, it pulls the next one up, which pulls the next one up, which pulls the next one up. But then when I jerk it back down, it gets pulled down, pulled down, pulled down, pulled down. And so this vibration travels up and down in this particular wave, but the wave travels end to end. Okay? So I'll play this through, and you can see that single wave pulse moves through the medium. Now watch one of these little green balls as the wave goes through. Okay? It goes up, back down. It did not go to the end. That's what I mean when I say a wave travels through a medium, but the medium doesn't move. Okay, and so send that pulse one more time. Okay, when it's done, you'll see this is just exactly the way it was before. So that was a disturbance. It moved through, and now everything goes back to the way it was. Okay, and that's the way waves work. So this is what that picture is showing, right? Force between adjacent particles causes that wave to propagate, and then once everything comes through it, the medium returns back to its original state. Okay, so we had an energy source, put in a vibration, vibration travels through the medium returns to where it used to be. Now, that's a little bit different than a continuous wave. Okay, this is a wave pulse, and we're going to do some labs where we study some stuff that's going on with that. A continuous wave has a continuously vibrating source or an oscillation, which we just got done studying, right? Could be a speaker bouncing up and down, could be the mass on the end of a spring, but there's some kind of continuous source that's causing it to go. And I want to show you one of these real quick. So I'm going to change this from pulse to oscillate. Mess with that a little bit. Now I've got this. If you watch this for too long, it'll make you sick, but I want to pause it, just whatever. Okay. This is a continuous wave, and I don't have just a single pulse, like this single pulse moving through anymore. Since the source continues to vibrate, the wave continues to vibrate. And if I take a snapshot of it, if I look at this wave in space, it looks just like a cosine or a sine wave. Starts here and oscillates up and down, up and down, up and down. The shape is a cosine wave. However, okay, let me restart this for a second. Okay, if you watch that, it looks like this thing goes from one end to the other, but the medium itself doesn't move. Okay, just the particles vibrate up and down. So concentrate on one of these little green dots. Okay, so here I picked this one. It's going up and down, up and down, up and down, up and down. It is not moving left to right. So in space, this does look like a sine wave or a cosine wave. But in time, if you concentrate just on one little piece in time, it's simple harmonic motion. It's an oscillation. It's just this motion being transmitted through the medium over and over and over and over and over again. Okay? So in space, a wave, sure, it looks like a sine wave. In time, it's just a vibration. Okay? So let's jump back over to these notes real quick. That's what the rest of this shows. Okay? It's just sine wave versus vibration. One individual particle moves up and down, and since this wave is moving left to right as that happens, we get the sine wave that occurs. Okay, we're going to be interested in describing then the properties of both of those. Okay, how fast does this vibration occur? How fast does this wave move left to right? Are those the same thing? That's kind of the next part of our investigation. Okay, so if I jump over to these, what we need is we need a way to describe waves. Okay, and let me pull up that animation again real quick. This is paused at a given instant in time. Now this dashed line through here, if that's our rest position, if I stop the oscillation and let everything come back to the way it was, then this wave will return to that rest position. This point up here, this point here, this point here, those are crests. Okay, this point here, this point here, this point here, these are troughs. So the crest is the maximum above, the trough is the minimum below, and the distance from the equilibrium or rest position to the top is the amplitude. It's exactly matched by this over here. Okay, so from rest to crest is an amplitude, or from rest to trough is an amplitude, which means the distance between a crest and a trough is actually twice the amplitude. Okay? So those are some major parts of a wave. The other thing we like to describe is period, frequency, and wavelength. Let's see. A wavelength is exactly what it sounds like. It's the distance between identical points on adjacent waves. Okay, so if this is where my wave starts, okay, then right here is where my wave ends. It's got one complete trough, one complete crest, and it's back to equilibrium. So the distance from here to here is a wavelength. Generally, it's easier to see that on minimums or maximums. So from one crest to another crest, or from one trough to another trough, okay, but any two identical points work. That's wavelength. It's denoted with the Greek letter lambda. Let me pull up the notes and I'll show you what I mean. Okay, so here, crests, troughs, I think you guys probably knew that already. Amplitude, knew that. Distance between two successive crests is wavelength, which is lambda. Okay, this thing right here, that's the Greek letter lambda. It's a lowercase. It sort of looks like an upside down Y. Okay, that's just the abbreviation we use. Okay, just like the source has a frequency, so does the wave. Okay, and it's the number of crests that pass by a point per unit time. Now, I'm going to play this. Okay, I'm going to turn the frequency down a little bit. I'm going to restart it. Okay, now I'm going to hold my mouse right here. There's 1, 2, 3, 4, 5, 6. So I'm counting crests that go by. And so if I knew how long that took, then I would have the frequency, right? That's all that means. Then period is just like before. Okay, if I pull this up, frequency is the number of crests that pass a point per unit time. Period is the time required for one complete wave to go by a point. So if I had a point on there and I timed it, okay, and I saw how long it takes for a crest and a crest, the next crest to come by, I would have period. But just like before, period and frequency are inverses of each other. Okay, so frequency is waves per second, period is seconds per wave. Okay. Now the last little thing I want to talk about here is the velocity of the wave. And I'm going to go back to the animation for a second. Okay. The velocity of the wave, and let me do that and send it down. The speed at which that pulse moves from one end to the other is the wave velocity. Okay. So we're not talking about how fast I jerk the wrench up and down. Okay. That looks like a mess. What we're talking about is we're talking about how long it takes for one crest to get from one point to another. Okay? So velocity is the speed of the wave, not the frequency of the vibration. So they're a little bit different, right? I can make this vibrate up and down really, really fast. Does that change how fast the wave moves from one end to the other? That's something we'll need to investigate. Okay? So wave velocity, or V, is not frequency, but how fast the crest moves through the medium. It describes the speed of the energy being transmitted, not the speed of the vibrating particles. Okay, and this leads us to an interesting formula. Since a wave crest travels a distance of one wavelength in a period of time t, so let me draw a picture for you here. Okay, a wave looks like this. Okay, and here's my equilibrium position. Now, this wave is going to propagate, and it's going to continue moving. So that means a second later, this thing will look like, or a split second later, depends on how fast the wave goes, it'll be shifted over here. And then a little bit later, it'll be over here. Right? And then a little bit later, it'll be over here. And a little bit later, it'll be over here. And eventually, okay, this crest will have shifted, or this point on this wave will have shifted all the way to here. It will have moved one entire wavelength, right? So it will have gone through the distance lambda. Now, since the wave occurs with or it takes t seconds for one wave to go by, what I actually know is how fast it's going. Since velocity is distance divided by time, it covers a distance of one wavelength in a time of one period. Okay? And since period is inversely related to frequency, I can replace this with V equals wavelength times frequency. Some of you might have seen that equation before. Okay? And so an example problem here, if a wave has a frequency of 3 Hertz, that means it oscillates up and down 3 times per second, or that's 3 waves come by this point in every second, right? So 3 crests come by this point in every second, and the wave is 5 meters long. That means the first wave comes by and then it moves this way 5 meters in the time it takes for the next wave to come by, and then 5 more meters so the next wave can come by, and then the third and final wave comes by, and my original crest is clear over here. It's moved 15 meters in that 1 second because it took, my frequency was 3 seconds. Okay, so 15 meters per second. V equals wavelength times frequency. Okay, waves are pretty neat. There's some cool properties we're going to start to investigate. For now, I want you to do the worksheet, and then that's it for the day.